Hello students, welcome to my lecture series on vector calculus. In the previous class, we have completed Gauss divergence theorem, applications and one example as a verification. In this class, I will discuss Green's theorem in plane. First I will give the statement of the theorem, then we will prove it. So, and again I said already, we will go through a simplest proof and we'll take 2 to 3 examples, and then finally we'll take 1 or 2 examples to verify the Green's theorem in a plane. Okay, fine. Our class will be on Green's theorem in XY, Green's theorem in a plane. That's it. So Green's theorem in a plane. Green's theorem in a plane. I'm sorry. Green's theorem in a plane. Yeah, let us see what is the statement of it. Let us see what is the statement of it. So Green's theorem talks about line integral into surface integral. So first of all, what is the idea behind this Green's theorem is, it talks about how to convert a line integral into surface integral in a plane. It is not the generalization. It is just applicable only for a plane. It is not for 3D. Only in XY plane, only in YZ plane, only in ZX plane, like that. So in a plane, the generalized theorem will be the Stokes theorem that will discuss how to convert a line integral into surface integral. So this is conversion of a line integral into surface integral just in a plane. Okay, so what this theorem says, let us first write the theorem statement. I write the theorem statement. Let S be a closed surface, S be a closed region in XY plane enclosed by a curve. Enclosed by a curve, let us name it as C. Enclosed by a curve C. This is the surface, then some region which has a boundary we call as a curve, by a curve C. Let P and Q be continuous and differentiable functions. Continuous and differentiable scalar functions. Differentiable scalar functions of X and Y in the region S. Then what it says, so this is the important thing we need to remember here. Then it says, so circulation of the quantity P dx plus Q dy is equal to surface integration of dou Q by dou X, dou P by dou Y dx dy. The line integral the line integral being taken around C such that S is on the left as one advances along the curve C. Okay, fine. So let us study the theorem. It is very simple. What it says here, you take some region. Definitely that region will have the boundary. We call it the curve. So for example, I'll take some boundary and it has some region. So this is the region. So that green color line we call as a curve, and this yellow color is the region, that is the surface S. Okay, so this is the surface S. Okay, fine. So this is the surface S and this will be the curve C. So as usual, P and Q will be the two functions in a plane. It is an xy plane, continuous, and they are differentiable scalar functions obviously. Then it says, so along the curve, we are taking along the curve Pxy dx plus Qxy dy. So this integration, so this entire quantity integration, along that curve will be is equal to this somewhat partial differentiation of Q with respect to x minus partial derivation of y with respect to y. That is surface integration in xy plane. That is what. So conversion of a line integral into a surface integral. The line integral being taken around C. So around C we have to take in such a way that S is on the left as one advances along C. Okay. So that I'll tell you. So whether we can do this circulation, either we can move in the clockwise direction or anti-clockwise direction. So of course now I am putting the arrows in the anti-clockwise direction. This will be the clockwise direction. So that I will explain you what is that left. So that means when I am going through the curve, surface must be on the left side instead of on the right side. Suppose if I go like this in the anti-clockwise direction, at all the time that will be on left side for me. So when I am here, so this is the left and this is the right. This is the right and this is the left. When I am here, this is the left and this is the right. When I am here, this is the left and this is the right. So it is always left hand side. That means we need to go in the anti-clockwise direction. So in the anti-clockwise direction. So this will be the statement. Then we will take the proof of it. Okay. So let us go to the proof of it. Let us go to the proof of this. So the proof of this as follows. The proof. So for this proof, we need to take some region in xy plane. Let's say I am drawing an xy plane here. This is y axis and this is x axis and y axis. So let us take some region. This is the curve. The red color will indicate the curve, which is bounded by some region S. So this is the region S. So I am taking this is the region S, and this will be the red color line indicates the curve. This will be the curve C. Now obviously it has the boundaries. So let's say this is the point where x is equal to a, and let's say this is the line x is equal to a. I can put like this. This is the line x is equal to a, and this is the line x is equal to b. x is equal to b, and this is the line y is equal to, let us draw a line which is, so I'm sorry, so this is the line y is equal to some, you can take some c, y is a b c, and this is the region, so y is equal to d, so y is equal to d. Okay, so I have taken lines, so let any line parallel to either coordinate axis cut the c at most 2 points. Obviously this is what actually, so this I have drawn the like this. So let curve have taken, and then the lines x equal to a, x equal to b, y equal to c, y equal to d we have taken. So we can write here, let s lie, that is surface S lies between the lines, you can mention here x is equal to a, x is equal to b, and y equal to c, y equal to d, y equal to d. Now so for this curve, so let us give some names here. I am giving the name of this point here, this is the region a, let us call it as a, let us call this will be some b, already c is given, next d and e, let us call this will be some d, let us call this will be e, it is like, so there is a part a, e, b, so when we are going like this, and this is we are going like this, so I already said anti-clockwise direction, move on the anti-clockwise direction, a, e, b and BDA, or otherwise ADB. Yeah. So now this bottom part and upper part, let us give the names of it for it. So I am giving the name for it. So let's say AEB is the one part. I'm sorry. AEB is one part. AEB, let us give this as the something, you can name it as, say y is equal to some f of x. This curve equation will be y is equal to f of x. Let us take this curve equation will be y is equal to some g of x. So y is equal to f of x and y is equal to g of x are the names of it. You can name it as, for this part AEB, you can call it as a curve C1, and this part will be curve C2, that I will mention here. Let y is equal to f of x be the curve C1. So curve C1 means that is from A, E, B. So and y is equal to g of x be the curve C2, that is of ADB. So lower part and the upper part. Okay, so you can say f of x is the lower part, that is less than or equal to g of x. Now you see here what we need to prove. So LHS is equal to RHS we need to prove, or otherwise RHS is equal to LHS we need to prove here. So let us take RHS. We'll prove here RHS will be is equal to LHS. So we'll take the RHS and we'll prove to the LHS. So this is the technique I'll adopt here. So in the RHS there are the two things, dou p by dou s, dou y, dou q by dou x is there. Consider any one thing. So let us consider this one, surface integral in xy plane of the factor dou p by dou y into dy dx. Okay, so this can be written as, first we will perform the integration with respect to y, then I will perform with respect to x. Here x is varying from a to b, but y is varying from So from the lower part will be f of x, that is y here. Then upper part will be g of x, that is y. So that is dou p by dou y into dy. So for this into dx. Now this entire thing will be, we can solve first this. So after that I simply get the p here. So that means what I'll get here. So this will be is equal to the integration from x is equal to a to x is equal to b. I'll get p there. Then upper limit and lower limit will substitute. P x y, but y is equal to g for the upper limit, minus p x y for the lower limit is f into dx. Okay, so this even can be written as separately. I'll write x is equal to a to b p of x g into dx minus integration from a to b p of xf into dx. Okay, fine. So now you observe clearly here. So I'll write here the b is the upper part. Let us write will be interchange the limits so that I can put the minus sign here. b to a p xg dx minus a to b p xf into dx. Now even further it can be written as, I can take the minus outside. Take the minus outside. So if I take the minus outside, then it will become, so take minus outside, then I'll write this one will be the first, minus outside, a to b p of xf dx plus b to a p of xg into dx. Now if you see here, there we have taken the curve will be like this, one upper part and the one with the bottom part. So this is a, e, b we are going. So we are going from x is equal to a to x is equal to b in the diagram. So that is, this is the curve corresponds to a to b. Then we are going from b to a on this g curve. This is the f curve and this is the g curve. So we are going from b to a. So finally these two together, this is the part 1, this is the lower part and this is the upper part. So total together what I'll have, total complete curve. So that means I can say here, this is the complete curve. I can circulate from a to b p xy dx. Okay, that's it. So finally what I have proved here, so surface integration of dou p by dou y dx dy will be is equal to this much. Okay, fine. Now similarly we can prove surface integration of dou q by dou x dx dy will be is equal to integration of, that is, you don't need to put here integration, I'm sorry, you don't need to put the limits here. So simply you can write here the complete curve. This is for complete curve. So for the complete curve it will be is equal to q of xy into dy. So finally if I subtract them, so this is what I can prove. Let us subtract them. If we subtract left hand side, what I have, surface integration of dou q by dou x, then subtract dou p by dou y into dx dy. So q of xy into dy plus p of xy into dx. So this is what. Okay, fine. So this is the simplest way of proving the Green's theorem. So remember here this, I'm sorry. So this Green's theorem in a plane, that is in xy plane or yz plane or zx plane, a line integration will be converting into surface integration, or surface integration will be converting into line integration. Okay, fine. So once again go through the proof how we did here, then I will take some problems. So this theorem statement will be closed surface, then line integral will be converting into surface integration. So for that purpose I have taken a region which is bounded between the lines x equal to a, x equal to b, and y equal to c and y equal to d. Then I divided into upper part of the curve and bottom part of the curve. I'm sorry. Upper part of the curve and bottom part of the curve. Finally I got like this. So whenever we are taking the RHS will be equal to LHS. There are two terms, dou p by dou y. Then I convert it. So finally like this. Then again dou q by dou x. Then finally we are converting like this and like this. This is the theorem. Okay, fine. So when this proof is over, then we will see some verifying some examples like this. Okay. Okay, fine. So now I'll take examples here. So let us go for the first example. First example as follows. Now let us take the problem. The problem will be as follows. Evaluate so along a curve, closed curve, the functions are as follows: cos x sin y minus xy dx plus sin x cos y dy by Green's theorem, where C is the circle x square plus y square is equal to 1. Okay, the boundary they have given, it is x square plus y square is equal to 1. So let us see the solution for this. So I have a xy plane. This is x-axis and this is y-axis. XY plane is there. So this is the solution. We will see the circle x square plus y square is equal to 1 in xy plane. So this is the x-axis and this is the y-axis and this is the center. And then this is the radius. They have given the radius will be of 1. Circle is of radius 1. X square plus y square is equal to r square. That is the radius is equal to 1. So what is our theorem says? Circulation. So p dx plus q dy must be is equal to surface integration of dou q by dou x minus dou p by dou y into dx dy. This is very well known for us. In our problem, this will be the p and this will be the q. So clearly, so what is p will be here? Cos x sin y minus xy. Then what is q will be here? That is sin x cos y. What is required here? From here I required dou p by dou y. So partial differentiation with respect to y, dou p by dou y. That is sin y differentiation is cos y. So I have cos x cos y minus x. Now here that q is equal to sin x, and then what I required here, dou q by dou x is required. So sin x differentiation is cos x, then cos y. Done. So I got this. Now substitute everything here. When I substitute there, and I need the LHS, that is entire thing. This is p dx plus q dy. That I will not do here. I'll do surface integration. So what is dou q by dou x? That is cos x cos y minus cos x cos y plus x into dx dy. So what will be here? Then cos x, this entire factor cancel. What is remaining for me? Surface integration x dx dy. Okay. So now we need to perform the surface integration along the closed curve. Okay. Then we do one thing. We'll use the polar coordinates. So we will convert this problem into polar coordinates. The circle polar coordinates is x is r cos theta, that is y is equal to r sin theta, r will be 1. Then what is dx and dy? That is area element. Dx and dy will be is equal to r dr into d theta. So, so this can be like this in a xy plane. So what you think of like this in xy plane? This is x-axis and this is y-axis. In xy plane, parallel to this. So this is the region. This is of dy and this is of dx. So in the circular region, we have, this is the region. This is the region. This arc length will be radius multiplied by this arc length. This is the arc length here. This arc length will be r d theta, and this will be the dr. This is r d theta, and this is dr, and this is dr. So length into width. That's why area element dx dy. Here it is same as that of r dr. Okay, fine. Now come here. The surface integration. X will be is equal to cos theta into dx. I am sorry, not in dx. We need to convert into r dr. R will be 1, dr d theta. So radius will be going from 0 to 1. Radius is going from 0 to 1. Angle theta is going from 0 to 2 pi. That is 360 degrees. So what I have here? dr will be 1, cos theta integration will be radius, you can put here radius, I am sorry, r dr, r will be there, that is r. So r integration will be r square by 2. R integration will be r square by 2. So x is equal to r cos theta, then r square by 2. So even you can put here as the parametric equation, x is equal to r cos theta, x is equal to r sin theta, then dx dy, then r is there, then r square will come here, then r square integration is r cube by 3, limits are from 0 to 1, then I have cos theta integration, that is sin theta, the limits from 0 to 2 pi. Here it is 1 by 3 and here it is, both are 0, upper limit 0 and lower limit is 0, answer will be 0. Okay, so this is the simplest example to understand what is this factor. Okay, so whenever sphere is there, cylinder is there, then it is better to use in the cylindrical coordinate, that is cylinder is there, cylindrical coordinates, sphere is there, spherical coordinates, that is polar coordinates, parametric forms will be useful for us. Let us go for the another problem. So another problem as follows. The next problem will be this. The next problem will be as follows. Show that the area bounded by a simple closed curve closed curve C is given by half into circulation of x dy minus y dx, and hence find the area of the ellipse given by x is equal to a cos theta, y is equal to b sin theta, where 0 less than or equal to theta less than or equal to 2 pi. Show that the area bounded by a simple closed curve C is given by, so that the area bounded by a simple closed curve C, that is the ellipse here, that is the ellipse, is given by, this is the area that is given by this much, this factor, and hence find the area of the ellipse. X is equal to a cos theta, y is equal to b sin theta. Let us go for the solution here. Then the given quantity we compare with the Green's theorem. The Green's theorem says p dx plus q dy will be equal to surface integration of dou q by dou x minus dou p by dou y into dx dy. So in our integration, this is a factor they have given. Let us call it as some okay. So here it will be half into dx dy can be written as, so p will be x by 2 and q will be, so p will be x by 2, so and q will be, I am sorry, x dy minus dx. So this is wrong, I have written. So it will be here p dx, that is p is minus y, and q is x. I require dou p by dou y, that is dou p by dou y will be of minus 1. I require dou q by dou x. Dou q by dou x will be 1. So this is some things. Now you substitute here. So even you can write it is x by 2 y by 2, that is y by 2, that is means 1 by 2, x by 2, that is 1 by 2. So this integration, that is p dx minus y by 2 dx plus q x by 2 dy will be is equal to surface integration of dou q by dou x, that is 1 by 2 minus dou p by minus 1 by 2, it will become plus 1 by 2 into dx dy. So from here what I'll have, the closed integration of minus y dx plus x dy divided by 2 is equal to surface integration of dx dy. Okay, fine. What is this integration of dx dy? Integration of dx dy. This is the area element, obviously. This is the area. This is the area. This is the area element. Integration of dx dy will be the. So this can be calculated. Area will be is equal to. This is the area. Then now that's what we need to calculate here. The area only we need to calculate. So substitute x value, y value. What is the x value and y value? I'll substitute. Y is given as b sin theta. So substitute the x value and y value, then we will get the answers clearly. Yeah. So y value will be b sin theta, that is minus b sin theta. So dx value will be minus a sin theta plus x value will be a cos theta, dy value will be b cos theta, whole divided by 2 will be is equal to area. So here it is minus minus plus, AB will be coming out, here also A is there, B is there, here also A is there. So that will be AB, and of course what I'll get here, we did a mistake here, minus A sin theta into d theta term is there, and here also d theta term is there. So finally, because when I have x is equal to a cos theta, then dx will become minus a sin theta into d theta. Similarly, when I have y is equal to b sin theta, dy will be is equal to b cos theta d theta. Okay. So finally, what I have here, sorry. So let us go down. So here circulation along the curve. So AB I can take out, then sin square theta plus cos square theta term will come, that is equal to 1 whole divided by 2 into d theta, that will be is equal to area curve. So that will be AB by 2 will come out, then circulation of d theta will be is equal to area. So for the entire circle, what is the answer I'll get? For the entire circle, the total angle will be 360 degrees, that will be is equal to area. So 2 cancel, pi AB will be the area, that is very well known thing to everyone. What is the area of the ellipse will be? Pi AB. Okay, so fine. This is the easiest way of solving the problems related to Stokes theorem. Sorry, Green's theorem in a plane. Stokes theorem will be the next. Okay, now we'll take one sum which is verifies, that is LHS will be equal to RHS. It will verify the Green's theorem by taking simple examples. So let us take the next example will be which verifies the Green's theorem. So next problem as follows. The problem will be like this. Verify Green's theorem in plane. Green's theorem in plane. For the integration across a closed curve 3x square minus 8y square dx plus 4y minus 6xy dy, where C is the region bounded by y equal to root x and y is equal to x square. So there is certain region that is bounded by y equal to x square and y equal to, that is y square is equal to x. Okay, so let us solve this problem. So before going to that, let us see what is that y is equal to x square and y is equal to that thing. So let us take this is the graphs of x axis, y axis. This is x axis and y axis. Y equal to x square first I draw. So that is everybody knows what is y is equal to x square. That is the y is equal to x square. It looks like this parabola. So then y square equal to x is again a parabola. That also very well known. That looks like this. Okay. This is the y square is equal to x, and this is a y equal to x square. So obviously here is the meeting point. That meeting point will have the 0, 0 coordinates, and here is the meeting point. That is that meeting point coordinates also we can determine. That is very easy to determine. How to determine that? So y is equal to x square, but y is equal to x square. Y square is equal to x. So in y square, do the square. that is x power 4. That is x power 4 minus x is equal to 0. One is x equal to 0 and x cube is equal to 1 I will get. So x cube is equal to 1. Anyway, we require the real roots, that is 1. So x is equal to 0 and 1. So here is the 1 1. So and they are asking the region will be, this is the region. This is the region they are asking. And this is the region. So our curve will be this. Surface will be this. Then our curve will be like this. We will go like this. Then we will come back like this. So this is our curve. So 0 to 1, then 1 to 0. So the bottom curve will be y is equal to x square and top curve will be y square is equal to x. Okay, when x is equal to going from 0 to 1, then y goes from something x, bottom curve root x, then top curve will be is equal to x. Bottom curve is y equal to x square, top curve is y equal to root x, like that. So okay, fine. So now go for the, so what is that we have? So P circulation of, so P dx plus Q dy will be is equal to surface integration in xy plane. So dou Q by dou x minus dou P by dou y into dx dy. So we need to prove LHS is equal to RHS. That means we need to solve this separately LHS and separately RHS. So let us take, divide, this will be like this. Divide the part will be like this. So LHS answer and RHS answer will be, should be same. Divide the problem will be like this. Okay, fine. Now first of all, let us take, this is the surface integration. Okay, so here what is P and what is Q? They have given P will be is equal to 3x square minus 8y square. Then Q they have given as 4y minus 6xy. Immediately I require from here dou P by dou y. Let us put the dou P by dou y partial differentiation with respect to y, that I will get minus 16y. Then here it is dou Q by dou x partial differentiation with respect to x, I will get as minus 6y. Now you substitute here and simplify. Then surface integration of dou Q by dou x, that is minus 6y. Then here minus of minus plus 16y. So then I will get 10y into dx dy. So that will be is equal to, then y is going from, x is going from 0 to 1, but y is going from, so y is going from, the lower curve will be of root x and lower curve is x square, then y is going from x square to root x, x square to root x into y dy, then dx. That's it. So when I integrate this, I will get y square by 2. The upper limit and lower limit I will substitute. X is weighing from 0 to 1. Y square by 2. Upper limit will be x minus x power 4 by 2 into dx. Okay, fine. So don't forget there is a 10. There is a 10. Now, so I will simplify this. When I integrate here, 10 by 2 will be the 5, x integration will be x square by 2, x power integration will be x power 5 by 5. Limits from 0 to 1, upper limit only contributes 1 by 2 minus 1 by 5, that is 3 by 10, that is answer will be is of 3 by 2. So RHS will be of 3 by 2. Now our aim is we need to prove LH is also is equal to 3 by 2. Let us prove here. Let us prove that will be is equal to 3 by 2. Let us go for the LHS part. So here is the LHS. So integration of the curve P dx plus Q dy. I am sorry. Just a second. So what is p dx plus q dy? So let's substitute p value, let us substitute q value and separately calculate the integration. So we need to calculate the closed curve here. So the bottom curve is y is equal to x square, y is equal to x square curve, and the top curve will be is of this. So the complete curve, this curve will be of y is equal to root x. Now so the line integral along the closed curve we need to perform. So first we need to perform this. So let us give the origin will be 0, meeting point will be some m you can take here. This is the meeting point or intersecting point. So we need to go for 0 to m along y equal to x square, then m to o along y is equal to root x, or otherwise y square is equal to x, both are same, y square is equal to x. Okay, so this we need to perform. So the line integral, let us take this entire integration, I will take as something, this entire integration you take as I. So that we need to take, I will be is equal to, so what we need to do, line integral of line integration along y is equal to x square, that is from 0 to m, o to m, plus line integration along y equal to root x, that is y square is equal to x from m to o. So this is the we need to perform. So it has a two parts. First we need to y equal to x square, then again the second part will be this. So let us call it the first part I will take as an I1. So second part will be I will take as an I2. I1 plus I2. Let us go for the first part I1. So the first part I1 will be is equal to what I1, y is equal to x square. Wherever y is there, there you put the x square. So I will do that job. So that means, so x is going from 0 to 1. X is equal to going from 0 to 1. X is going from 0 to 1. So wherever y is there, the first term will be 3x square. Don't do anything, 3x square. But here 8y square is there. But y is equal to x square, that is 8x power 4 will come. Then there is a dx, don't do anything, dx only. Then plus, then what is there? 4y, but y is equal to x square. Let us put 4x square. Then minus 6xy, that is minus 6x cube. Then dy is there, but dy will be 2x into dx. That's it. Okay, fine. Then I1 will be is equal to, now try to integrate 3x square integration, 8x power 4 integration, then even before integration 0 to 1, let us align all the terms properly. 3x square minus 8x power 4, then 8x cube minus 12x power 4 with respect to x. The x cube integration x cube by 3, x power 4 integration is x power, so minus 8x power 4 minus 12x, so minus 20x power 4. So that means even further it will become, then further it will become, so I1 will be is equal to 0 to 1, 3x square plus 8x cube minus 20x power 4. I1 will be is equal to x cube by 3, 3 cancels, only x cube, x power 4 by 4, that is 2x square, 4x power 5. So the limits will be from 0 to 1. That is lower limit anyway will not contribute, only for upper limit 3 minus 4, that is 3 minus 4 will be minus 1. So with that we have finished the first part of the problem. So now go for the I2. I2 is the same integration but along the curve y equal to root x. So now for I2. Now for I2. For I2 that is the same closed integration but wherever y is there, there you put the root x. Y equal to root x. The first term, then you don't need to do anything here. that is integration along the curve where x is equal to going from 0 to 1. First term you don't do anything, 3x square as it is. Second term 8y square, but y square is equal to x, that is minus 8x into dx, you don't need to do anything, plus 4y, but y is equal to root x, that is 4 root x, minus 6xy, but y is equal to root x, that is 6x power 3 by 2 into dx. So dx we need to write here, just a second. So that dx will become, as y is equal to root x, then dy will become, so 1 by 2 root x into dx, that is dx upon 2 root x. So now I2 will become integration from 0 to 1, write properly. The first term is 3x square, next term is 8x, the next term is divide with 2 root x, that is only left is 2, then divide with 2 root x, 3x square will be there. So 2 1 ja, 2 3 ja, root x cancel, that is 3x. So limits from 0 to 1. Now integrate this. So when I integrate this, what I will have? 3x square minus 11x plus 2 integration. The integration, the first is 3x square, that is x cube by 3, 3 cancel. Then 11x square by 2, that is minus 11x square by 2, that is minus 11x square by 2. Then plus 2x, limits from 0 to 1. Only upper limits contributes, lower limit will not contribute. So 1 minus 11 by 2 plus 2. Okay, so that will become 3 minus 11 by 2, 6 minus 11 by 2, 6 minus 11 by 2 means 5 by 2. The answer will come as here 5 by 2. And what is the overall answer? That we want. That is the overall answer we want. I is equal to, so I1 plus I2. I1 plus I2. I1 I got as minus 1 plus 5 by 2. That is 3 by 2. So we have proved that LHS will be is equal to RHS. With this, the theorem is verified. That means that's what actually the initially we do. We need to verify the theorem. Okay. So we need to verify the theorem. I already said. We need to verify the theorem. So okay, fine. Here, as we need to verify the theorem, this is what. So this is the curve and everything we have taken. Okay. So RHS directly we calculated and I got the answer will be 3 by 2. So here you may have the doubts, sir, why we taken from y equal to x square to y is equal to root x instead of 0 to 1, as y also going from 0 to 1. So you remember here, as the x is going from 0 to 1. So x is going from 0 to 1. Then who will decide the y? Now you draw a line parallel to here. This is the area integration we are calculating. This is the y is starting and this is the y is ending. Here y is starting means x square. Here y is ending means root x. That is the limits will be as x goes from 0 to 1. So at any instant of x, let's say some instant of x, then what is the y? Y is ranging from x square to root x. This is the way of finding the limits that I already told you when we have discussed the surface integration. Okay, so I hope rest of the part is very clear. Okay, fine. So the next class we will see the further Stokes theorem. In Stokes theorem also we use the Green's theorem proof and all these things. So because in Stokes theorem is the generalized form. So that generalized form is again important, that also will be useful to convert a line integral into surface integral. So okay, fine. Thank you. Thank you very much.